Hello. In the previous clip we took a look at Nyquist stability theory and how it could be employed to determine the stability of a closed loop system, or more generally how can it be employed to determine whether the zeros and poles of a given complex function f of s is within a certain bounded region, a region bounded by a curve C in the complex plane. Now how do we mathematically establish Nyquist stability theory? To mathematically establish the theory we need two concepts. One is the notion of analytic functions and the second is what is known as the Cauchy integral formula. So let us briefly define what analytic functions are and then subsequently also state Cauchy's integral formula and then use both to establish Nyquist stability theory. If a function f of s is infinitely differentiable within a region omega bounded by the curve C, then f of s is said to be analytic at all points within omega C. So if the function f of s is complex differentiable at all points and we should be able to differentiate it as many times as we wish, then we call such functions as analytic functions within this region C. So what are some examples for analytic functions? If you take f of s to be equal to s minus a, then we see that f prime of s is equal to 1, f double prime of s equal to 0, and that is equal to all other derivatives of s for n greater than or equal to 2. So we see that this function is infinitely differentiable, and this is infinitely differentiable regardless of which specific point we are evaluating it at. On the other hand, if you were to look at a function of the kind f of s is equal to 1 by s minus a, and if a happens to be a point that belongs to the region omega which is bounded by the curve C, then we see that it is not differentiable at the point s equal to a, because this function blows up at that particular point, but it is differentiable at every other location. So what we can say therefore in this case is that f of s is differentiable, is analytic everywhere except at s is equal to a. So it is a fairly straightforward concept. If a function is differentiable, then it is an analytic function. If it is not differentiable at certain points, then it is not an analytic function. We shall employ this notion of analytic functions to now state Cauchy's integral theorem. The theorem states that in a region omega bounded by the curve C, if f of s is analytic everywhere, meaning that it is differentiable everywhere, then 1 by 2 pi j times the contour integral over the curve C of f of s by s minus a ds is equal to f of a if the point a belongs to the region bounded by the curve C, and is equal to 0 if a does not belong to the region bounded by the curve C. So this is Cauchy's integral theorem, and we shall employ this theorem along with the notion of analyticity as we have defined above to now prove Nyquist stability theory. To prove Nyquist stability theory, let us evaluate the integral 1 by 2 pi j times the contour integral of f prime by f ds, where f is the function that we are interested in, namely 1 plus g of s, where g of s is our open loop transfer function. We want to determine how many of the zeros of f, which are essentially the closed loop poles, are on the right half of the complex plane. So we undertake the contour integral of f prime by f, and since Nyquist stability theory is a general theory that is not applicable only to determine stability, but more generally to determine if the zeros of f are inside this closed contour C or not. C can be any contour in the complex plane. Now we see that we can write this integral as 1 by 2 pi j times contour integral over C d of log of capital F, because by definition d of log of capital F is f prime by f times ds. And we can subsequently further simplify this expression by noting that log of capital F is equal to log of magnitude of f times e to the power j angle of f, and this in turn is therefore equal to log of magnitude of f plus log of e to the power j angle of f. This in turn is equal to log of magnitude of f plus log of e to the power x is essentially x, so therefore this is going to be equal to j times angle of f. Therefore we can rewrite this integral as 1 by 2 pi j contour integral over C d log of f as equal to 1 by 2 pi j contour integral over C d log of magnitude of f plus 1 by 2 pi j contour integral over C j times d of angle of f. Now if you notice this integral, since our contour integral essentially looks at d of log of magnitude of f and starting from some particular location s on this contour and then goes round that contour once, we see that the initial and the final magnitudes of f are identical. Therefore d log of magnitude of f integrated over the contour will be equal to 0. This integral will not be 0, d of angle of f will be the net change in angle of f, and I shall call that delta of angle of f, and I have the two terms j, one in the numerator rather than the denominator. So by cancelling those I would get this to be equal to delta of angle of f divided by 2 pi. Now we know that 1 by 2 pi j times the contour integral of d of log of f can also be written in a slightly different manner by noting that our f is equal to 1 plus g of s, and by factorizing this we can write this as some constant times s minus p1 times s minus p2 and so on and so forth up to s minus pn, where p1 to pn are the n zeros of 1 plus gs, which are also the closed loop poles of our system, divided by s minus p g1, because these are the poles of g of s, times s minus p g2 and so on and so forth up to s minus p g n. Since we can write f in this particular manner, we note that log of f will be equal to log of constant times s minus p1 times s minus p2 and so on and so forth up to s minus pn divided by s minus pg1 times s minus pg2 and so on and so forth up to s minus pgn, which in turn can be expanded out as log of k plus log of s minus p1 etc etc up to plus log of s minus pn minus log of s minus pg1 and so on and so forth up to minus log of s minus pgn. Therefore, we would have d of log of f to be equal to d of log k plus d of log s minus p1 and so on and so forth, plus d of log s minus pn minus d log s minus pg1 and so on and so forth, minus d log s minus pgn. Now we note that d log k is going to be equal to 0 because k is a constant. So if I were to compute the contour integral 1 by 2 pi j over c d log f, I would get this to be equal to the contour integral over c times 1 by 2 pi j times d log s minus pi summation I going from 1 to n minus summation I going from 1 to n d log s minus pgi. So both the summations are within the contour integral. Now we note that d log s minus pi for any index I is essentially going to be equal to ds by s minus pi. Therefore, we can simplify this contour integral as being equal to 1 by 2 pi j times contour integral ds by s minus pi sigma I going from 1 to n minus 1 by 2 pi j times contour integral over c sigma I going from 1 to n ds by s minus pgi. Now if we look at any one of these terms, contour integral over c ds by s minus pi, we note that it is of the form contour integral f of s by s minus a ds with the particular function f of s being chosen equal to 1. Therefore, if the point pi is inside the contour c, we would have this term ds by s minus pi to be equal to 1. If pi belongs to omega of c. If on the other hand, if pi is not part of the region bounded by the curve c, this is going to be equal to 0. Therefore, I would have 1 by 2 pi j times contour integral over c sigma ds by s minus pi to be equal to, when I going from 1 to n, to be equal to k, where k of the closed loop poles, which are the zeros of f of s, are inside the contour c. Likewise, 1 by 2 pi j contour integral over c sigma I going from 1 to n ds by s minus pgi will be equal to L, where L is the number of poles of the open loop system, which are also the poles of f of s that are inside that contour c. Therefore, we would have that this expression 1 by 2 pi j contour integral d of log of f to essentially be equal to k minus L. So if you remember from the previous slide, we found that this expression 1 by 2 pi j contour integral d log of f is also equal to delta of angle of f divided by 2 pi. And this, putting these two together, we are able to establish Nyquist stability theory, which states that delta of angle of f divided by 2 pi is equal to k minus L, where L is the number of open loop poles inside omega c and k is the number of zeros of f of s inside omega of c. So, delta f, which is the net delta of angle of f, which is a net change in the angle of f divided by 2 pi, is essentially the number of encirclements of the complex number f of the origin in the f of s plane. Therefore, the number of encirclements of the origin in the f of s plane when the complex number s is made to go round the contour C once is equal to the number of closed loop poles, which are essentially the number of zeros of capital F of s, minus the number of open loop poles, which are the poles of the open loop system. This in effect establishes Nyquist stability criterion, although in this particular form it is applicable for any other contour C as well. So, this contour need not necessarily be the right half of the complex plane, but could be any contour in the closed contour in the complex plane, and this statement can be employed to determine how many of the closed loop poles are inside that contour and how many are outside that contour. What is worth noting once again is that this number of encirclements does not directly give us the number of closed loop poles, which are the zeros of f of s that are inside omega c. It only gives us the difference between the number of closed loop poles and the number of open loop poles. Now, how do we then get the number of closed loop poles separately? To do that, it is assumed that we know the number of open loop poles that are inside that contour C, and that is assumed to be known because the open loop system is something that we have designed. So, either from first principles or from certain strategically conducted experiments, it is assumed that we can determine how many of its poles are inside that contour C. With that knowledge, we can then look at the number of encirclements and then determine how many of the closed loop poles are inside the region omega of C. There is just one more point that I want to make regarding the number of encirclements. These encirclements could either be clockwise or anti-clockwise. So, which one do we take? To answer this question, one needs to simply note that if we take the variable s in the complex plane in the counterclockwise direction, then the statement for Nyquist stability theory would be that the number of counterclockwise encirclements of the origin in the f of s plane would be equal to the number of closed loop poles minus the number of open loop poles. On the other hand, if we chose to take the variable s in the clockwise sense, then the statement for Nyquist stability theory would be that the number of clockwise encirclements of the origin in the f of s plane for points s on the contour C would be equal to the number of closed loop poles minus the number of open loop poles. So, depending on the direction along which we take the complex number s around the contour, we need to look at the direction in which we are encircling the origin in the f of s plane. Now, as we discussed, the real utility of this theory is not from its ability to determine the location of closed loop poles in some specific closed region C, omega of C, but rather to determine the stability of the closed loop system. To determine the stability, all that we need to do is to pick this C to encompass the entire of the right half of the complex plane. So, if I were to draw the complex plane here, then we distort this curve C to be a very large curve whose one edge is very close to the imaginary axis, but does not exactly coincide with the imaginary axis, and the other side is a large D-shaped curve, and the radius of the semicircular D-shaped curve R is tended to infinity, so that we are able to cover the entire of the right half of the complex plane and check whether any of the poles of f of s would be in this plane, in this side of the complex plane or not. Now, in this case, we choose to take the variable s in the clockwise sense, although in some of my previous demonstrations we took it in the anti-clockwise sense. In this case we choose to take it in the clockwise sense, and having taken S along this contour in the clockwise sense, we now look at the number of clockwise encirclements of the origin in the f of s plane. So what is f of s? F of s is essentially 1 plus g of s. So if I were to draw f of s plane, I would have the real part of f of s and the imaginary part of f of s here. I now look at the number of encirclements of the origin in the f of s plane. What is available to us from experiments is g of s, and we have to undertake this extra calculation to compute the complex number 1 plus g of s. In order to avoid this extra computation that we would have to undertake, what is commonly done is to look at the encirclement of not the origin but rather the point -1, 0, not in the f of s plane but rather in the g of s plane. So if I were to plot the real part of g of s versus the imaginary part of g of s for values s on this contour C, I would get some curve, and I look at the encirclement of the point -1, 0 of this curve, which is exactly identical to looking at the encirclement of the origin in the f of s plane. So to minimize this computation of 1 plus g of s given g of s, I simply look at the encirclement of the point -1, 0 in the g of s plane rather than looking at the encirclement of the origin in the f of s plane. So what we shall have to do in order to determine the stability of the closed loop system is to plot g of s for values of s along this D shaped contour and look at the number of times it encircles the point -1, 0 in the g of s plane. Now what are the kind of values that s would assume on this contour? Since this straight edge of the contour is very close to the imaginary axis, along this contour we would have s to be equal to j omega. Now along the D shaped contour, since it has a radius r and is centered at the origin of the complex plane, we would have s to be a complex number of the form r e power j phi, where phi is this particular angle. Now since we are dealing with transfer functions which are generally strictly proper, in other words the degree of the numerator polynomial is always less than the degree of the denominator polynomial, we see that g of s for s of the form r e power j phi, where the radius r is tended to infinity in the limit r tends to infinity, will be essentially equal to 0. So therefore all the points on this D shaped contour will collapse to the origin in the g of s plane, simply because my g of s, which would be of the form s power m plus b1 s power m minus 1 and so on by s power n plus a1 s power n minus 1 and so on, where n is greater than m, will assume a value 0 in the limit r tends to infinity. So what we are left with therefore is to simply compute g of s for values of s on this straight line. Now for the part of the straight line which starts from the origin and goes all the way to j infinity, our g would be of the form g of j omega, since s would be equal to plus j omega on that straight line. On this straight line however, which starts from minus infinity and comes to the origin, we would have s to be equal to minus j omega. So we would be evaluating g of minus j omega. However, there is a further simplification that is possible by noting that since g represents the transfer function of a real system, when we write it down as a ratio of two polynomials as we have done here, we note that all the coefficients a1, a2, a3, b1, b2, b3 and so on are all real numbers, and what that indicates to us is that g of minus j omega would be equal to g of j omega bar, where g of j omega bar represents the complex conjugate of g of j omega. In other words, if I were to graph g of j omega for omega going from 0 to infinity, then g of minus j omega will look very similar to this curve, with the exception that this curve will be reflected about the real axis. So therefore, we do not even need to obtain g of j omega along the negative imaginary axis, because that curve will be simply a mirror image of the curve that we would obtain for omega going from 0 to infinity. So what is therefore generally done is we would simply compute real part of g versus the imaginary part of g for omega going from 0 to infinity. A typical curve might look something like this. It might or might not encircle the point -1, 0, and it will collapse to the origin, because all the points on this d-shaped curve would get mapped to the origin in the g of s plane, and for points that are on the negative imaginary axis, the curve would simply be a reflection of this curve about the real axis. So we can easily complete the entire Nyquist plot if we simply evaluate it for omega going from 0 to infinity. And this curve g of j omega for omega going from 0 to infinity is called the Nyquist plot. And by looking at the encirclement of the point -1, 0, we can tell the difference between the number of closed loop poles and the number of open loop poles that are on the right half of the complex plane. So to look at the practical utility of Nyquist stability theory, let us take a few numerical examples. Let us say that g of s was equal to 1 by s plus 1 times s plus 2 times s plus 3. Firstly, we note that there are no open loop poles on the right half of the complex plane. The open loop poles are at -1, -2 and -3, so they are all on the left half of the complex plane. Therefore, this represents a stable open loop system. To determine whether 1 plus g is stable or not, we plot g of j omega for omega going from 0 to infinity and look at the encirclement of the point -1, 0 in the g of j omega plane. So if we have to compute g of j omega, we substitute s is equal to j omega and we get the expression to be 1 by j omega plus 1 times 1 by j omega plus 2 times j omega plus 3. We note that when omega is equal to 0, so if we were to plot real part of g versus the imaginary part of g, we note that when omega is equal to 0, we would have the g of j omega to be equal to 1 by 1 times 2 times 3, which is 1 by 6. Now 1 by 6 is a positive real number, which indicates that it is a complex number with phase equal to 0 and magnitude equal to 1 by 6. So we locate it on the real axis, positive real axis of the g of j omega plane, and this is the point 1 by 6. Now as omega goes from 0 to infinity, we note that the magnitude of each of these terms, for instance 1 by j omega plus 1 would be square root of 1 plus omega square. The magnitude of 1 by j omega plus 2 is going to be 1 by square root of 4 plus omega square. The magnitude of 1 by j omega plus 3 would be 1 by square root of 9 plus omega square. So it is a monotonically decreasing function of omega, and in the limit omega goes to infinity, this magnitude also tends to 0. What about the phase? The phase would be equal to, the phase of the first term would be equal to minus tan inverse omega. The phase of the second term would be equal to minus tan inverse omega by 2, and the third term would be equal to minus tan inverse omega by 3. So when omega is close to 0, all these terms are close to 0. When omega tends to infinity, each of these terms go to pi by 2, which implies that the net phase of g of j omega as omega tends to infinity, angle of g of j omega in the limit omega goes to infinity will be equal to minus pi by 2 minus pi by 2 minus pi by 2, which is going to be equal to minus 3 pi by 2. In order to obtain the real axis and imaginary axis crossings, we determine the location at which the imaginary part of g of j omega goes to 0. This is for real axis crossings, and the real part of g of j omega equal to 0 will give us imaginary axis crossings. In this particular case, if we were to expand out by multiplying the 3 terms, we would have g of j omega to be equal to 1 by minus 6 omega square plus 6 plus j times 11 omega minus omega cube. Therefore, the real axis crossing would happen when the imaginary term is 0, which implies that 11 omega minus omega cube should be equal to 0, which has a solution omega equal to 0 as one solution, the other being omega equal to square root of 11. So, if we substitute omega equal to square root of 11 and compute g of j omega, we will be able to determine the location at which the Nyquist plot crosses the real axis once more. It crossed once at omega equal to 0, which we already saw. It is going to cross again when omega is equal to square root of 11. Likewise, to determine the imaginary axis crossing, we set the real part to be equal to 0, which implies that minus 6 omega square plus 6 would be equal to 0, or in other words omega would be equal to plus 1. We ignore the negative term because we are only looking at omega being positive going from 0 to infinity. So, we substitute omega equal to plus 1 and compute g of j times 1, that will allow us to locate the point at which it crosses the imaginary axis. If we join all these points by a dotted curve, then we would get the final Nyquist plot. The phase goes from 0 to minus 3 pi by 2 and it crosses the imaginary axis at omega equal to 1, it crosses the real axis at omega equal to square root of 11. And it so happens that in this particular case it avoids the point minus 1 comma 0. So, since we have no open loop poles on the right half of the complex plane and the Nyquist plot is not encircling the point minus 1 comma 0, we conclude that the system 1 plus g of s has all of its zeros. In other words, the closed loop poles of the overall system, namely g of s by 1 plus g of s, are all on the left half of the complex plane. Now, let us take one more example. G of s is equal to 1 by s times s plus 1. Now, there is a small problem with this particular example, namely that the point s is equal to 0 is a pole of g of s and it happens to also be a point on the contour C. So, we want to make sure that none of the poles of our open loop system are on the contour C, in which case we cannot evaluate the integral, contour integral, and apply the Cauchy integral formula for such a case. Therefore, what we do, since we have an open loop pole that is on the contour C, we distort the contour a little bit near the origin by choosing a semicircular path that avoids this point s is equal to 0, and the radius r of that semicircle would be tended to 0. So, it is very small, but it just avoids the point s is equal to 0 and ensures that this contour does not have any poles on its on itself. Subsequently, the rest of the contour would be exactly as it was in the previous case. The D-shaped contour with radius r tended to infinity would be exactly the same as before, and the rest of the contour would be very close to the imaginary axis exactly as before. So, what we would do in this case, is that we would evaluate g of s, where s is equal to j omega for this part of the contour, and then for the semicircular part we compute g of s, where s would be of the form s is equal to r e power j phi, where if we zoom into this region, I will dot a semicircle in a slightly magnified form. Our contour C avoids the origin and then goes further up. We define this angle phi to be the angle made by some point S on this small D shaped contour of radius r with the real axis. Now, since we would have once again g of s to be equal to g of minus s to be equal to g of s bar for all points on the contour, we need to consider phi going from 0 and up to pi by 2. So, we compute g of s for s is equal to r e power j phi for phi going from 0 to pi by 2, and we likewise compute g of s for s is equal to j omega for omega going from 0 to infinity. Omega will not be exactly 0, omega will start at value r and go to infinity, and the r, the radius r of course is tended to 0. So, if we first compute this term g of s for s is equal to j omega, we would have it to be of the form 1 by j omega times j omega plus 1. The magnitude of g of j omega would be equal to 1 by omega times square root of omega square plus 1. The angle of g of j omega would be the angle of 1 by j omega plus the angle of 1 by j omega plus 1. The angle of 1 by j omega is minus pi by 2. It is always a purely imaginary number on the negative imaginary axis, therefore it is always minus pi by 2, and the angle of j omega plus 1 by j omega plus 1 will be equal to minus tan inverse omega. Now, if you substitute s is equal to r e power j phi, we would have g of s to be equal to 1 by r e power j phi times r e power j phi plus 1. We note that since r is tended to 0, r e power j phi plus 1 will approximately be equal to 1. Therefore, g of s will simply be equal to 1 by r e power minus j phi. So, g of s would therefore be a circle of radius 1 by r, which is a very large number since r is tended to small r is tended to 0, and the angle will change from, since phi goes from 0 to pi by 2, the angle of g of s will go from 0 to minus pi by 2. So, if you were to sketch the Nyquist plot for this case, we would have for the first part g of j omega, omega going from small r to infinity. When r is very small, g of j omega will be of the form 1 by r times square root of r square plus 1, and that is going to be a very large number, and the phase is going to be close to minus pi by 2. So, we start here, and then the final phase as omega tends to infinity will be equal to minus pi by 2 minus another pi by 2, therefore minus pi. So, the Nyquist plot would look something like this for this part of the curve. Now, for the other part, the phase would start at 0 and go to minus pi by 2. So, that curve would look something like this, and the radius of this is going to be equal to 1 by small r. The full Nyquist plot is obtained by reflecting this Nyquist plot about the image real axis. That is going to look something like this. And we see that this curve always avoids the point minus 1 comma 0, and we have no open loop poles on the right half of the complex plane. So, our closed loop system 1 plus g of s, the zeros of 1 plus g of s will always be on the left half of the complex plane. So, our closed loop system will always be stable. We will look at one final example. We shall take g of s to be equal to 1 by s square times s plus 1, in which case once again, since we have two poles of the open loop system at the origin, we have to undertake a similar distortion to the D shaped contour exactly as we had done for the previous example. So, this is how our D shaped contour is going to look. We would have a tiny semicircular region of radius r tended to 0, and this big D would have a radius capital R which is tended to infinity, and these two straight lines are close to the imaginary axis. So, we once again compute g of s for values of s on this straight line and on this tiny semicircular part, and then plot it. So, if you were to do that, we would see that the phase of this transfer function starts at an angle that is close to, that is slightly greater than minus pi. So, when we are near the origin somewhere here, our Nyquist plot the value would be somewhere here, and then as omega tends to infinity, g of s tends to 0. So, it would approach the origin in this particular manner, and on this tiny semicircular patch we would have s to be equal to r e power j phi, and when we substitute it in this expression, we would have g of s to be equal to 1 by r square e to the power 2 times j phi times 1 by r e power j phi plus 1. So, this term 1 by r e power j phi plus 1 is approximately equal to 1. So, g of s would be equal to 1 by r square e to the power minus j 2 phi. Since we would have phi going from 0 to pi by 2, we would have 2 phi going from 0 to pi and minus 2 phi going from 0 to minus pi. Therefore, we would have this part of the curve being mapped to this particular semicircular arc, and for the rest of the curve we just have to take the reflection of this part about the real axis, and that is going to look something like this. And the point minus 1 comma 0 will always be inside this contour, and we see that this contour encircles the point minus 1 comma 0 twice. So, this part encircles it once and that part encircles it once more. So, it encircles it twice, and we have no open loop poles on the right half of the complex plane. So, what it indicates is that a closed loop, the closed loop system whose denominator polynomial will be 1 of 1 plus g of s, will always have two closed loop poles. On the right half of the complex plane. On the right half of the complex plane.